1A. Draw the Lewis structure for the molecule indicated below. Show all lone pair electrons in formal charges. B. Draw the line angle formula for the molecule. And C. What is the most electronegative atom in the molecule? So we can start off with the Lewis structure. What's nice about this molecular formula that's given is that all of the important functional groups are already grouped together, so we can kind of just go from left to right and draw it out. And we need to keep in mind that carbon can only form 4 bonds because that's a full octet, and we have to draw in the lone pairs. So we can kind of check to see if each atom has a full octet by just kind of thinking of each bond as 2 electrons. So carbon has 2, 4, 6, 8. That's a full octet. That's a full octet. This is a full octet. This is a full octet. Hydrogen can only form 1 bond, so that's okay. But oxygen only has 2 bonds, but it needs 4 more electrons to be satisfied, so we have to add 2 lone pairs. And now that we have the Lewis structure, we can easily draw the line angle structure from it. Basically, every carbon is a vertex, and you don't have to draw the hydrogens, so we can start off with the methyl groups. And however, we do have to draw the other functional groups. So there's an alcohol group here, and we just draw it like this, sticking out from the left. And we don't have to worry about lone pair electrons on the line angle structure. And for part C, what is the most electronegative atom in the molecule? We can just see oxygen is the only one with lone pairs, so that's the most electronegative atom. 2. Trabectedin, sold under the brand name Yondelis, is an FDA-approved drug for the treatment of advanced soft tissue sarcoma and ovarian cancer. It was initially discovered in an extract from a sea squirt, but later determined to be produced by a fungal symbiont living inside of it. Label the indicated functional groups. So unfortunately, this is sort of a memorization heavy question, but there are some things that can point you in the right direction. So we can just go in order, starting with A. A is an alcohol group because it has a R group attached to an OH, where R is an alkyl or an aryl group, and it's bonded to this OH or hydroxyl group. So you can also write hydroxyl as well. B is an amine, and we know this because as long as you look for the nitrogen, it's most likely an amine group. It's a benzene or arene ring. It's a 6-sided ring with alternating single and double bonds. D is a sulfide, and we know this because we're just looking for the sulfur atom. And E is an ester, not an ether, and the way we can tell these apart is that ethers look like this, and this R prime means it could be a different R or alkyl or aryl group, while esters look like this. And as you can see, there's some similarities. Both of them have 2 alkyl or aryl groups attached, as you can see R and R prime in both of these. But the difference is that esters have 2 oxygen atoms bonded to it, and also one of the oxygen atoms has a double bond, whereas ethers only have 1 oxygen atom, and it's the only bonds in this whole functional group are single bonds. And here we see that there's 2 oxygen atoms, and one of the oxygen atoms is double bonded, so this is an ester and not an ether. 3. Indicate the bond angles, molecular shape, and hybrid orbitals of the indicated atoms. So first we can recognize that this molecule is being represented by a line angle structure, not a full Lewis dot structure. So we might want to draw in the lone pairs and the hydrogen atoms that we need to make our job easier for this problem. So let's start with atom A. It's pointing at a carbon atom, and this carbon atom has 4 bonds already, so we don't need to draw in any lone pairs or any hydrogens. Um, Atom B is pointing at a nitrogen atom with 3 bonds, so it needs 1 lone pair or 2 electrons to form a full octet. Because keep in mind, each bond you can kind of think of it as 2 electrons. So 2 times 3 is 6, and then adding a lone pair of 2 electrons, that would be 8, and that's a full octet. Atom C, it's pointing at another carbon, and this carbon has 2 bonds shown, one to an oxygen and one to another carbon. So we need to draw in 2 hydrogen atoms to fill the octet. And now we're ready to start the problem. So for atom A, it has 3 electron domains because there's 1, 2, and 3, since one of them is a double bond. So this is a trigonal planar shape. And we need to remember that trigonal planar has a bond angle of 120 degrees and a hybridization of sp2, since there are a total of 3 electron domains. Atom B is a nitrogen with 4 electron domains, since there are 3 bonds, and then there's 1 lone pair, so that's a tetrahedral shape, which has a bond angle of 109.5 degrees and a hybridization of sp3, since there's 4 electron domains. And atom C is another carbon atom. It has 4 bonds and no lone pairs of electrons, so it has a tetrahedral shape because there are 4 electron domains. And again, this has a bond angle of 109.5 degrees and a hybridization of sp3 because there are 4 electron domains. 4a, provide a chemically reasonable resonance structure for the molecule below using the arrow pushing convention to depict the flow of electrons. Include all lone pair electrons and formal charges. B, circle the resonance structure that is the major contributor. And C, provide a brief justification, 1 sentence or less. So before we do anything with the arrow pushing, we need to draw in the lone pairs for some of these atoms. We know that all of these carbons do not need any lone pairs drawn in because they all have 4 bonds, which is a full octet. And the hydrogens can only form 1 bond, and they're all bonded to a carbon, so that's also fine. We don't have to do anything there. So the only 2 atoms we need to do anything about are oxygen and nitrogen. Oxygen has 2 bonds, and normally it has 6 valence electrons, so 6 minus 2 equals 4 electrons left for a full octet. And that means we can draw in 2 lone pairs, since each lone pair has 2 electrons for oxygen. For nitrogen, it has 5 valence electrons normally, and here it has 3 bonds. So 5 minus 3 equals 2 electrons that need to be drawn in, which is just 1 lone pair. So now we're ready to draw the arrow pushing mechanism. So we can already see that there's a double bond here and a double bond here. And we also know that electrons always move from areas of high density to areas of low density. So a neat way to do this is to just move this double bond over here and then push this over here. Keep in mind that every time you add a double bond to carbon, or you add a bond to carbon that already has 4 bonds, you need to move one of them away and then turn that into a lone pair. So now we can draw in the resonance structure, which is just the same thing, but the double bond is just placed somewhere else. And I guess we can also draw in the lone pairs. So now we know that this this bond turned into a lone pair, which is 2 electrons, so we can draw an extra lone pair on this oxygen. This nitrogen is the same, it still has 1 lone pair and 3 bonds. This carbon has 3 bonds and no lone pairs, so now we have to do the formal charges. If you remember from Gen Chem, there's an easy way to do this. We just take the number of valence electrons the atom should have, and then minus the number of electrons, the number of lone pair electrons it has, and then minus the amount of bonds it forms. So let's start with oxygen. This oxygen should have 6 valence electrons, but here we see it has 6 lone pair electrons, so 6 minus 6 is 0, and then it also forms 1 bond with carbon, so 6 minus 6 minus 1, which is equal to a 1 minus or a -1 charge. Or you can just write it as a single minus sign. And then here, this carbon should have 4 valence electrons. This carbon has 0 lone pairs of electrons and 3 bonds formed with other atoms. So that is a 1 plus charge, or just a plus. Now we have to justify and circle the resonance structure that's the major contributor to the resonance hybrid, and that would be this one, because it has a lower formal charge overall. (5a) Provide the IUPAC name of compound A shown below. Indicate stereochemistry if appropriate. B. Is carbon A a primary, secondary, tertiary, or quaternary carbon? So before we can get to naming this compound, we have to recognize that these methyl groups are wedged, which indicates the possibility of chiral centers at carbons A and B. So let's go and figure out if they are indeed chiral centers. So carbon A has 2 methyl groups attached to it. These are the same groups, and we can't assign RNS stereochemistry to it because they would have the same molecular weight. So carbon A is not a chiral center. We can move on to carbon B. Carbon B has 3 different groups attached to it, substituents, and obviously it also has a hydrogen in the back that's dashed, which we don't really care about because it's always the lowest molecular weight. So now to get to the RNS configuration part, we need to first number these substituents according to their molecular weight, with 1 being the highest and then 3 being the lowest. We know that this isopropyl group is the largest, so it has the highest molecular weight. This ethyl group is the second largest, and the methyl group is the third largest, and hydrogen is the fourth, but we don't really care about that. So we can recognize that this is kind of going up in a clockwise fashion, which is characteristic of the R configuration. So we can go ahead and put that in our name. And the RNS configuration will always come before the rest of the name. And normally we would want to put a number in front of the R or S, so for example, 1R or 2S, etc., etc. But in this case, since there's only 1 chiral center in the whole molecule, we do not need to do that. Although you can if you want to, but I'm not going to do that. So now it's probably a good idea to number this parent chain. We can obviously tell that this is the longest chain, so it is the parent chain. We have 2 options of numbering it. We can either start 1 from here on the left or 1 from here on the right, but we should start on the left because this allows for these methyl groups to have the lowest numbers, which is what we want. So let's go ahead and do that. So now we know that the methyl groups are numbered 2 and 3, so we can write 2, 3. And since there's 2 of them, instead of writing methyl, we can just write dimethyl. And we've already previously established that this is a 5-carbon long chain, parent chain. So this is a pentane. And now we need to figure out what kind of carbon carbon A is. Is it a primary? Is it a secondary, tertiary, or quaternary carbon? So carbon A has, well, it's attached to this methyl group. It's attached to this methyl group, and then it's attached to whatever this is, which it's also attached to a carbon. So a methyl group, that's one carbon, so that's one. That's another carbon on this methyl group, and then this is a carbon. The last thing it's attached to is a hydrogen, but we don't count that. When we're determining primary, secondary, etc., we're just counting the number of carbons that this carbon in question is attached to. And since it's attached to 3, that would be a tertiary carbon. 5C, provide the Newman projections for compound A looking from carbon A to B for both the overall highest and overall lowest energy states. Carbon A should be the front carbon. Be sure to consider stereochemistry if appropriate. So I've already moved down compound A over here so that we can more easily see it and not have to go flip between pages or anything. And first, before I draw the Newman projections, what I like to do is to redraw this in a more linear way so that's easier to see all of the substituents. So I will label carbon A bonded to carbon B. There's always going to be 4 bonds to each carbon, and there's two methyl groups bonded to carbon A. And then in the middle, there's a hydrogen. And the same with carbon B, except this time it's an ethyl group, a methyl group, and hydrogen. So with this, we can move on to drawing the Newman projections. There are 2 types, like overall types of Newman projections. There's a staggered type and an eclipse type. For the lowest energy projection, we always draw a staggered projection because the substituents for the front carbon, the back carbon are further apart, so there's less interactions between them, so it's less reactive and there's lower energy. So let's go ahead and draw that. And likewise, for the highest energy Newman projection, it would be the opposite, where we would want to draw an eclipsed formation, because if the substituents for the front and back carbon are eclipsed, they're closer together, they're more likely to react, and thus there's higher energy state. And keep in mind that carbon A should be the front carbon. So this would be the front. So I guess we can just put in the substituents however we want to. It doesn't really matter. I'm just going to keep it the same for both the highest and lowest energy Newman projections to make it simple. And now we can work through the back carbons. So for the lowest energy projection, we want to make sure the biggest groups are separate from each other to avoid the interactions between them. So a trick that I learned was to just keep the same groups diagonal from each other. So for example, we have this hydrogen, right? And there's a hydrogen in the front carbon. So then we can just place this hydrogen directly diagonal from the front one. And then similarly, there's a methyl group in the back carbon, and there's one in the front carbon. So we can put that methyl group here. Lastly, there's an ethyl group. There isn't another ethyl group on connected to carbon A, so we just put this here, and that's okay, because we're just trying to minimize the interactions between the different substituents, especially the bigger ones, but we can't completely eliminate them, but that's okay. For the highest energy Newman projection, we want to keep the large substituents close together. So here we see that the hydrogens are diagonal from each other, but here we want to keep them eclipsed to each other. And similarly, for these 2 methyl groups, we want to keep them close to each other. And then finally, there's an ethyl group. There isn't another ethyl group in the front, but we can just place it next to the methyl group because they're both large substituents. 6. 1,3-dimethyl cyclohexane can refer to several stereoisomers. Draw a structure of the cis and trans isomers each. So first, we need to recognize that we're just given a name of the molecule. We're not given a structure, like a line angle structure. So it might be a good idea to draw that out before we do this problem, just so we can see what it looks like. So we know that it's a cyclic alkane, and it's a cyclohexane, so there will be a 6 carbon ring, so it's like this. And there are 2 methyl groups indicated by the dimethyl, and they are at positions 1 and 3. And it doesn't really matter where you place these, but you just need to place them 2 carbons apart, or 1 carbon apart actually. So let's see, if you start naming from over here, you can do this carbon is carbon 1, this is 2, and this is 3. So you can place a methyl group here and a methyl group here. So that's our molecule. So now we can draw out the trans isomer and the cis isomer. For the trans isomer, these methyl groups just need to have different stereochemistry. So one of them has to be wedged and one of them has to be dashed. So you can either draw something like this, or you can draw something like this. And keep in mind, these are basically the same molecule because if you flip it around, mirror image and all that, it's going to be the same. It doesn't really matter what you draw, but there are multiple answers, and I just wanted to show that. Now let's move on to the cis isomer. For the cis isomer, cis means same, so both of the methyl groups have to be dashed or both of them have to be wedged. So there's also 2 different ways to draw this, and I'll draw those out. This is the cis isomer where both of them are wedged, and then this is the cis isomer where both of them are dashed. 7a. Name the molecules shown below. Indicate stereochemistry if appropriate. So we're given this molecule. It's a cyclohexane, and immediately we recognize that there are 2 potential chiral centers because of the wedges and dashes of the substituents, so I'll label that right here. And we need to determine whether or not they are indeed chiral centers before we can name this molecule. So let's go from left to right. The left carbon, it's not a chiral center because, as you can see, there's 2 methyl groups sticking out of it, and we can't assign RNS stereochemistry if there are 2 of the same substituents because they would have the same molecular weight. So this rules out the left carbon as being not a chiral center. Now let's look at the right carbon. So the right carbon also has a hydrogen bonded to it. It's dashed, it's in the back. And let's just check if there's an internal plane of symmetry, because if there was, it would not be a chiral center. And there is not an internal plane of symmetry because, as you can see, the left side of this plane has these 2 methyl groups, whereas the right side does not. So we can indeed assign RNS stereochemistry to this chiral center. So let's go ahead and do that. You can write out all of the atoms that are bonded to these carbons to assign the RNS stereochemistry, assign the numbering of the molecular weight, but you don't really have to do that. An easier way to do it is to just look at the bulkier side. So first, we can see that this side is bulkier than this side, which is bulkier than this side, because this left part has half of the cyclic alkane with the 2 methyl groups attached to it as well. So that gets number 1 as being the highest molecular weight. The second highest molecular weight would be this bond because it is bonded to the other half of the cyclic alkane, this cyclohexane. And then the third highest molecular weight would go to the methyl group that's sticking out of it. And obviously hydrogen is the fourth, but it's always number 4, so we don't really care about it. And as we see that the numbers are going up in a clockwise fashion, this is characteristic of an R stereochemistry. So we can go ahead and write that in the name. And again, since there's only one chiral center that we identified in this compound, we do not have to assign numbers to the R or the S or whatever. So we can just move on to the next part of naming, which is numbering the substituents. There are two possible ways to number it. You can either go from one being on the left or one being on the right. And you would want to do, this one's a bit tricky, but you would prefer to have the one on the left because there are two of these groups. So then both of them would get the lowest possible number, which is 1. If you did it the other way around, these groups would both get 3, and we don't want that. We want as many groups as possible having the lowest numbers possible. So this would be 1, this would be 2, and this would be 3. And these are all methyl groups, so we're just going to write 1, 1, 3. And since there's 3 methyl groups, it is a trimethyl. And as you can see, it's cyclohexane. There's 6 carbons, and it's a ring, so it's cyclohexane. Seven B, draw the lower and higher energy chair conformation for compound B showing all axial and equatorial substituents. So I've moved down compound B from the previous problem over here, and I've also copy and pasted this chair conformation reference image that you unfortunately do have to have memorized. You just need to know the positions of the equatorial and axial substituents. So these blue hydrogens, these are the equatorial ones. They are pointed away and they're less likely to react, and therefore they have a lower energy. And then these red hydrogens are the axial hydrogens, and they're pointed up, and as you can see, they can react with each other. They're more closer together, and this would contribute to a higher energy chair. And just to note, wedge substituents will either be up or up and out. So like this is up, and then this one is an example of up and out. On the other hand, dash substituents will either be down or down and out. So this would be a dash substituent. This would also be a dash substituent. So with all of that said, we can now draw our chair conformations. There's 2 major ones we care about. There's the left-handed and the right-handed chair conformation. So let's go ahead and draw that. It's kind of difficult to draw, but you get the hang of it eventually. And as we previously established, this carbon that's attached to 2 methyl groups was assigned the number 1. This is number 3, and then we can just fill out the numbers like so. And now we have to number our chair conformations. So what I like to do is put 1 in one corner and 4 in the other corner first, and then just fill it out so that it goes in ascending order. And then the tricky part is doing this for the other chair conformation. And something just a trick I learned is that if the 1 is originally on this first chair conformation you drew, and you put the 1 in the lower left corner, you would put it in the upper left corner of the next one. And then if the 4 is on the upper right corner, you would put it on the lower right corner. And then, as we can see, 2 and 3 are in the front. We will keep those in the front. And 6 and 5 are in the back, and we keep those in the back. And that's how you properly draw the chair conformation. And now we can fill out the methyl groups that are on these chairs. So we see that for carbon 1, there's both a dashed and a wedged methyl group. And as we can reference from over here, this is how it looks like on the reference image. So the wedged methyl group, that's going to be the upper one. So that's going to be up and out. And then the dashed will be behind, so it's going to be down or down and out. In this case, it's just down. And then on our number 3 carbon, there's another methyl group, and it's going to be up and out because it's wedged, so it's in front. So it has to be up or up and out. In this case, it's just up and out. And then for our other chair, we can do the same thing, but keep in mind that's going to be different because we have to look at these different positions of the equatorial and axial substituents. So for carbon 1, there's the same 2 methyl groups, and one of them is going to be up and one of them is going to be down and out. And then next on carbon 3, there's a methyl group. It's going to be just up because it's wedged, and that's what it shows on this reference image. So now we can go ahead and assign which one of these is the lower energy chair and which one of these is the higher energy chair. And by doing that, we just have to count the number of equatorial slash axial substituents. So in this case, on this chair, there's 2 equatorial substituents, and then there's 1 axial substituent. And then this chair has 2 axial substituents and only 1 equatorial substituent. And the axial substituents are closer together and they're more likely to react. So this would be the higher energy chair because there's more axial substituents as compared to this other chair that we drew. So I'm going to move that over to the higher energy chair box. And then likewise, this would be the lower energy chair because there's fewer axial substituents as compared to the other chair conformation we drew. A compound C is an HIV protease inhibitor known by the trademark name lopinavir. A. Assign R or S to the 2 stereocenters numbered 1 and 2. B. Calculate the total number of stereoisomers. For B, you may leave your answer in the form of the equation. So first, we need to figure out the R/S stereochemistry for these 2 chiral centers. And since we're given this big this big molecule, I think it's easier to just draw out the chiral centers separately. So I'll show you what I mean by that. So let's take chiral center 1, for example. I'll just draw it similar to the Newman projection, but not entirely. There's a alcohol group in front, and then likewise there's a hydrogen in the back that is kind of irrelevant. It's always last, we don't really care. And then on this right side of the alcohol group, there's a carbon bonded to a hydrogen, a nitrogen, and another carbon. So we can just write that out. It's going to be carbon first, and then a hydrogen, a nitrogen, and another carbon. Likewise, on this side, this is a carbon that the carbon is bonded to, and it's bonded to 2 hydrogens, and then it's bonded to another carbon. Now that we've written out all of these atoms, we can assign the numbers to them. So we have to look at the first atom in the list and then just compare these. Obviously, carbon and carbon are the same molecular weight, and oxygen is a higher molecular weight than carbon, so this alcohol group gets number 1. Since we can't compare a carbon with another carbon, we cross that out and we move on to the next atom, which is a hydrogen and a hydrogen. And once again, they're the same, so we can't compare those, and we move on. Then the next one in the list is nitrogen versus another hydrogen, and in this case, nitrogen is the greater molecular weight, so that gets number 2, and then this top group gets number 3. And as you can see, this is moving in a counterclockwise fashion, which means that chiral center 1 has a S stereochemistry. Now let's do this again with chiral center 2. I'm just going to move this to give us more space. Chiral center 2 is a bit trickier because this nitrogen group is in the back, it's dashed, and then the hydrogen would be wedged. But that doesn't really change much about how we do this, and you'll see why. So we can kind of just put the hydrogen somewhere in the somewhere on this thing. We can just put it here, I guess. And then we can see that um, this carbon is bonded to this isopropyl group, so we can write out carbon, and then it's hydrogen, and then there's two methyl groups. And then on this side, there's a carbon bonded to an oxygen, and then a nitrogen. So carbon, oxygen, nitrogen. And like we did before, we can just compare the first atom of each of these. Hydrogen is going to be last, so we're just going to assign this 3. Carbon and carbon is the same thing. We cannot compare two of the same things, so we move on. And now it's between a hydrogen and an oxygen. The oxygen will be the greater molecular weight, so this will be 1, and then this hydrogen containing group will be 2. And this, as you can see, this is going in clockwise fashion, so it's R stereochemistry. But wait, because this hydrogen is actually in the front, since it appears R, it's actually S. So both of these chiral centers are S chiral centers. For the total number of stereoisomers, which is part B, there is a formula that we learn is 2 to the n, where n is the total number of chiral centers. And we can just kind of count these out. So obviously, there's going to be this one and this one, which are given to us. This is not a chiral center because there are 2 of the same methyl groups. This is not a chiral center either because it has a double bond. This is a chiral center because there's 3 different groups, and then there's a hydrogen in the front. This is not a chiral center. This is a chiral center. This is not a chiral center because there's 2 hydrogens. Those are the same. So we have these 4 that are chiral centers. And then again, this is not a chiral center either because it has a double bond. So the formula, we're going to plug in n equals to 4, so 2 to the 4th. You can either leave your answer like that, or you can calculate it. It's just 16. 9. Compound D is an SSRI derivative known by the trademark name Zoloft. Provide the enantiomer and 1 diastereomer for compound D. So, as we previously learned, enantiomers are just the same, but all of the dashes are changed to wedges, and all of the wedges are changed to dashes. In this case, there are these 2 that are both wedge substituents, so we just need to change both of them to dashes. And you have to make sure that all of the stereocenters have the changed stereochemistry if you're talking about an enantiomer. So I'll just go ahead and draw that. And now for the diastereomer, you only have to change one of these to a dash because a diastereomer retains some of the same stereochemistry from the original compound, but some of the other ones are changed. So there's 2 ways you can draw it. You can draw it like this. Sorry, this is pretty hideous. Or you could draw it like this, where it's the other one that's flipped or inverted. The problem only asks for 1, so either of these are okay, and I'm just drawing both to show that there are 2 ways you can do the problem. 10. Which of the following molecules are chiral? Circle all that apply. We can just go in order from left to right. starting with this first one. This first one is achiral because if you rotate it around this bond, because remember that alkanes or single bonds have some freedom of rotation, it will just turn into this molecule, HO. This is a meso compound because there's a internal plane of symmetry down the middle, and so this is achiral because meso compounds are achiral. Now let's move on to the second one. This can be redrawn in a better way, I would say a better way, because I kind of find it difficult to tell whether a molecule is chiral or not just based on Newman projections, so I like to draw it in a more like line structure angle way. So this is the same as this. And the reason is that you can recognize that these two are diagonal from each other, this OH group and then this hydrogen that is reflected here. They are trans. And then on the other hand, these are also opposite each other because they're also trans. They're just diagonal from each other. And then these two ethyl groups are also trans. They're like across from each other. And as we can see, this kind of looks hard to decipher at first, but remember that you can rotate around this bond because it's a single bond. And then we can see that it kind of turns out like this. And you can rotate this around many, many times, and you'll never be able to get a meso compound. So even though these two carbons have the same substituents, they're ordered in a way that you'll never get a meso compound. So this molecule is chiral. Now let's move on to the third one. This is a pretty straightforward one. It's not a meso compound, but it's a cyclic ring, and if you draw a line down the middle, there is an internal plane of symmetry, so it's achiral, even though there's a substituent here and then a substituent here. For number 4, for this molecule, this is a chiral molecule because even though you can rotate this around and potentially try to make a meso compound, it's not going to be a meso compound because these are different. You will only get a meso compound if the substituents on both sides or both carbons are the same substituents. So this is a chiral molecule. Finally, we have this chair conformation, and like I said before with Newman projections, I don't really like looking at chair conformations either. I think it's kind of easier to first draw it out as a line angle structure, so I'm going to do that. As you can see, there's 2 methyl groups, and I'm just going to number it 1, 2, 3, 4, 5, 6, giving the lowest numbers to the methyl groups. And then I'm just going to redraw it, and it looks kind of like this. And you know that it's both wedged because this is just up, and then this is up and out. So they're going to be both wedged substituents or wedged methyl groups. And as you can see, like the previous cyclohexane, there's also an internal plane of symmetry here. So this is an achiral molecule. 11. Provide the structures of 4 constitutional isomers with the molecular formula C6H12 in line angle formula. So for this problem, I think the obvious go-to is just a cyclohexane, and I'll just draw that in and I'll show you why. Each of these is a carbon, and there's going to be 2 hydrogens attached to each carbon. And 6 times 2 is, obviously it's 12, so that would be C6H12. And then just a trick I learned. I don't know if they want you to do this, but I think it's fine since it's still the right answer. Is you can get the same molecular formula by just moving one of these carbons outside and forming a chain outside the cyclic alkane. So this first one we have a cyclohexane. The next one we can just draw a cyclopentane, and then just put a bond or like a carbon on the outside. The next one we can draw a cyclobutane and then add another carbon to this outside chain. And then the final one we can draw a cyclopropane and then add yet another carbon to this growing chain on the outside. And we can just count the hydrogens to make sure they are correct. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is right. For the cyclobutane, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this would also be right. And then for the cyclopropane, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. As you can see, they all have 6 carbons and 12 hydrogens, so these would all be correct constitutional isomers for this molecular formula. And as always, there's like tons of ways you can do this problem. This is just my way of doing it. I think it's the easiest, but who knows? 12. Threonic acid below is a sugar acid derived from the sugar threose. The L isomer is a natural metabolite of ascorbic acid, vitamin C, using the following choices: enantiomers, E, diastereomers, D, constitutional isomers, CI, or identical, I. Identify the relationship between the molecules below. If no relationship exists, place an X in the box. So we can just go from left to right in this order. The first molecule that we're shown is a diastereomer because only one of these wedges is inverted to a dash. The second one is an enantiomer because both of these wedges are inverted to dashes. The third molecule is a bit trickier, but you can just rotate it. Keep in mind that there's also a wedged hydrogen here. And remember that single bonds have freedom of rotation, so you can rotate around this bond and you'll get the same thing. You'll get something like this. And this is identical to this molecule, so this is identical. And then for the last molecule, it also looks a little bit tricky because at first it looks like it's a different molecule, but in fact, if you flip it once vertically and once horizontally, you'll see that these two are the same molecule. Everything is placed in the same way, so this would also be identical. 13. Draw 4 resonance structures of this cation. So we know that this carbon has a positive charge, and then there's these 2 double bonds, obviously. And basically what we can do is every time you move the double bond over here, or just kind of just move it over one spot, the positive charge will be displaced and it'll go somewhere else. And we can just kind of draw 4 resonance structures going in a clockwise fashion, just moving the double bond around. So first we can move this double bond up here, and this will displace the positive charge and move it somewhere else. So now the double bond will be here, and this other double bond is not touched. It's going to stay like that. And keep in mind that there's 2 possible, ways you can put the positive charge, but you can't put it here because this carbon already has 4 bonds to it, so it can't have the positive charge. So you'll put the positive charge over here. Now we can draw another resonance structure, and we can move this other double bond that we previously did not touch. We can move it here to displace this positive charge, and we can redraw that like this. and this positive charge would be on this this carbon. And we can do that again. We can move this upper double bond over here and displace this charge again. We get something like this. And then finally, we do this one more time. We can move this double bond back here and then displace this positive charge here. And we'll get something like this. This is 1, 2, 3, 4. Oh, sorry. This is where the positive charge ends up.